Similar objects are objects which are the same shape, but generally are of different size. A basketball and a baseball, for example, have the same shape, but they're certainly different in size. A model ship and a real ship are similar objects as well. Now, an important consideration is corresponding parts. Corresponding parts are parts in similar objects which occupy corresponding positions. For example, the rudder on the model ship would correspond with the rudder on the big ship. The flagpole on the model would correspond with the flagpole on the real ship, and that kind of thing. Now, here's the idea, though, mathematically, that we want to pursue a little bit. Ratios of corresponding parts are equal. And in these two triangles, notice, are the same shape, but they're different sizes. And we can set up various ratios and actually proportions here between these two. Here's what I'm talking about. And there are a lot of right ways to do this. We can say that 2 corresponds to 6, or the ratio of 2 to 6 is the same as the ratio of, let's say, this side to that side. You see, now I'm using corresponding parts between the two triangles, and that's equal to this side over that side, or 3 over 9. Now notice that all of these are, this is 2 over 6, well that reduces to 1/3. 4 over 12 reduces to 1/3. 3 over 9 reduces to 1/3. You see, so these are all equal to one another. And there's another way to look at the situation. We can say that, gee, the ratio of the short side to the bottom side, that is the side with 2 and the side with 3, is the same thing. You see, the ratio of this side to this side in the small triangle is equal to the ratio of this side to that side in the larger triangle. So it's 6 to 9. And sure enough, if we reduce this, it becomes 2/3. So these are indeed equal. Now we can use these ideas in order to solve problems like this. Suppose we have a couple of triangles and take a look at the labeling. And we'd like to find x. We'd like to find the bottom side of this triangle. Now you might be thinking, gee, I'm not sure that these are similar yet. Well, similar triangles would have the same size angles in corresponding positions. And here we see an angle of 65 degrees and here an angle of 25 degrees. Well, what does that have to do with anything? Well, it turns out, though, that we can calculate the size of this angle. 90 minus 65, that's 25. So this is a 25-degree angle, you see. And over here, I can find this angle. 90 minus 25 is 65. So that's a 65-degree angle. So sure enough, these two triangles are similar to one another. If all the angles of one triangle are equal to the corresponding angles of another triangle, they're similar. They're going to have the same shape, you see, but they may be a different size. Okay, now we can use the idea of our ratios in order to find x. And here's how we do that. And there are a lot of right ways to do it. You might think, well, gee, one way to do it is to say 4 corresponds with 7. 4 corresponds with 7 in the same way as 8.6 corresponds with x. Another way to set it up, another relationship that will get us to the same position, is to say that 4 corresponds to 8.6 in the same way as, now I did the short side here over 8.6, so it's over here 7 corresponds with x. Other relationships, I could have flipped this one over. I could have said 7 corresponds with 4. You see, I could have said 7 corresponds with 4 in the same way as x corresponds with 8.6. So if I flip this one over, I would have to flip that one over. And in a similar way, if I flip this one over, I could flip that one over, and I would get the same result. Now, how do we deal with these the equations like this? Well, it turns out that the fastest way to deal with equations like this, and notice that there's a single fraction here and a single fraction here. The regular way is to clear the fractions by multiplying through by a common denominator, but the shortcut is this. Now this is called a proportion, by the way. We have a ratio set equal to another ratio. Ratio is just a fraction. We can think of it like that anyway. And to solve a proportion, we can cross multiply. That's the shortcut. Now if I multiply along this diagonal 4 times x, I have 4x. And if I multiply along the other diagonal, I have 7 times 8.6. Now, I'm confident that from here we can go through and solve this. The answer, though, to me right now is not terribly important. It's the setup and the development of how to solve it that's so very important. Now, look at what happens over here. When I cross multiply, I get 4 times x, 4x, if I multiply along this diagonal first. And then I go along this diagonal and I have 7 times 8.6. Now notice in both situations I end up with exactly the same looking equation once I have cross multiplied. And as long as we're setting up our various ratios, our correspondences, you see, correctly, we'll get this same kind of result. We'll get a result where the equation in every different situation will look pretty much the same, and we'll get the same result as we might expect. Okay, we won't finish through with this, but I'm sure we can multiply these and then divide by 4 and find an answer in the problem. Another kind of relationship between objects is this, that we talked about similar objects as being the same shape but different in size. Congruent objects, though, have the same shape and the same size. So similar objects, same shape, different size. Congruence means same shape, same size. So they're like, it's kind of like one of these can fit on top of one another, if we're talking about plane figures like triangles and such. So one triangle can fit exactly onto another one. A lot of geometry is associated with proving the congruence of triangles. Now, there are a number of ways of doing it, but I'm going to show you 2 of them here. This is the side, side, side rule, sometimes abbreviated SSS, and it goes like this, that 2 triangles are congruent if 3 sides of one triangle are equal to the corresponding sides of the second triangle. Now, this almost seems eminently obvious, doesn't it? I mean, that they would have to fit onto one another or have the same shape and the same size if the lengths of the sides are identical. You see, and that's all that this is saying. And to kind of illustrate how this congruence idea might work, you might think, well, gee, how can I make them not equal? Let me try to make them not equal. I'll take a 3, 4, 5 triangle here, and I'll take sides. Maybe I've got little sticks or little popsicle sticks, let's say, or something like that, and I make them 3, 4, 5. And I don't care what the unit is. It could be inches or feet or whatever. But so I have sides of 3, 4, 5. Now let me put these sides together. Let me just put this in with that and that in with this and just put them together. Now, do I have a triangle? Must I get a triangle that looks exactly like that? Sure. It might not be configured quite this way. I mean, we might say, well, let's take the side 3 and put it right here. And let's take the side 5 and let's put it right here. You see, and let's put 4 up here. You see, so I might have kind of a different twist on it. And let me see. Gee, I'm confusing myself here. I think this is where the right angle goes. Well, it should go right there. Let me see. I drew it incorrectly. But what I'm trying to show is that you might have a situation where, you see, it kind of looks upside down from the first one or something like that. Here's the 3, here's the 4, here's the 5. And we saw this as a right triangle before. But although these might be twisted from one another or flip-flop from one another, well, certainly we could take one of them and move it over and twist it around and turn it over, and it will fit exactly on the other one. And that's what congruence is all about, that corresponding sides, the sides are equal to each other, the angles are equal to each other, and that kind of thing. All right, here's another rule that's used to show that triangles are congruent. It's called the side angle side rule, and it's abbreviated SAS. 2 triangles are congruent if 2 sides and the included angle of one triangle are equal to the corresponding parts of the second triangle. So we don't have to have all 3 sides equal if we have 2 sides and the included angle. But it turns out that if we have 2 sides and the included angle, then it kind of predetermines that third side, the length of that third side, doesn't it? So if we have that kind of congruence between 2 triangles, then we have that kind of correspondence and equality of corresponding sides and angles, then we have congruence. Now, here's a situation where we might be using this notion of Well, one of these notions, let's say, in order to show that these two triangles are congruent. Can we show these to be congruent? Gee, they kind of don't look like it because they're like twisted from one another. But look at the labeling. We have a 7-foot side here. We have a 7-foot side here. We have a 4-foot side here. We have a 4-foot side here. We have an angle of 50 degrees and we have an angle of 50 degrees. And the important thing is not that we have those items, but that they are arranged in a particular way. That is, the angle is between the two sides. You see, that's important. And the angle is between those two sides over here. So we have the correspondence necessary for the SAS rule. And we would say it something like this, that we would say, well, let's see, AB is 7 feet. So it means that AB is equal to this 7-foot side over here, which is DF. We have the angle here at A equal to the angle here at F. And we have the 4-foot side here, which is AC, and it's equal to the 4-foot side here of EF. Now, notice that we have the idea of a side, angle, side. So by the SAS rule, these two triangles are indeed congruent. Here's a classic problem involving similar triangles. It involves the idea that we can measure the height of some very tall objects without actually going to the top of those objects. For example, if we have a big tree here, we can measure the height of the tree without climbing the tree. If the sun is shining, and we can measure the shadow. And here's how it works. Suppose we can measure the shadow of the tree, and suppose we measure the shadow from the center of the tree out here to the end of the shadow to be, let's say, 18 feet. That distance is 18 feet. Now, where in the world do the similar triangles come in? Well, it goes like this. What we do is we take an object that we can measure, a smaller object, let's say a yardstick, and we stand this yardstick up, let's say over here, and the yardstick will cast a shadow that we can measure, and let's say the shadow of the yardstick is 2 feet. Now, we know that the yardstick is 3 feet tall. And the similar triangles come in because of the angle at which the sun is shining on the tree and on the yardstick. You see, for the tree, we have a triangulation like this, where the sun is shining and casting the shadow like this. So we have this right triangle. You see, and with the yardstick and its shadow, we have a similar kind of thing. So the angle that's formed here at the top of the yardstick and the angle formed at the top of the tree is exactly the same. The triangles then are both right triangles and they are similar. So let's see, we can set up these correspondences then to find the height of the tree, which I'll label as X. Now, there are a couple of great ways to do this. One way is to say, well, let's compare. Let's write the ratio of the height of the tree to the shadow of the tree and set that equal to the height of the yardstick to the shadow of the yardstick. So here's what we're doing. Height over shadow equals height over shadow. And it's really important to have the correspondence the same in both of these. If height is on top over here, it needs to be on top over there. That's the idea. So for the tree, let's see, we have X for the height and the shadow is 18. For the yardstick, 3 is the height and the shadow is 2. And now we just solve this. And the solution is found by cross multiplying. That's the fast track way. X times 2 is 2X. And on the right, we have 18 times 3. Well, 3 times 18 is 54. And dividing on both sides by 2, we find X to be 27. And that's 27 feet then for the height of the tree. Now, there's another way to set up the relationship between the two triangles. Now, the first way that we said was height over shadow. Now, it could have been the other way around. It could have been shadow over height. But if we think shadow over height for the tree, we need to think shadow over height for the yardstick. All right, so that's the idea. Now, here's another correspondence, though. We could go between the two triangles. You see, we could say that the height of the tree corresponds with the height of the yardstick in the same way as the shadow of the tree corresponds with the shadow of the yardstick. Let me show that mathematically over here. So it's height over height, shadow over shadow. But remember that if we have the tree's height in the numerator here, we have to have the tree's shadow in the numerator over here. That's the correspondence that has to be correct. So here, let's see, the height of the tree over the height of the yardstick. The shadow of the tree, shadow of the yardstick. And notice that when we cross multiply, we get the same result that we did before. X times 2, 2x. Then 3 times 18 is 54. And working down, we find once again that the height of the tree is 27 feet.